Okay, this is lecture number 26, even though it says 25. Okay, a couple admin things, a quick review, and then one example problem. So let's get to it here. Slide this down. Okay, so for the I made a mistake on the last PowerPoint presentation. I said the information on the study guide was negotiable. So that's not really negotiable, but the information on the study on the cheat sheets is negotiable. So take a look at those. If you think something should be on there, let me know. I'll certainly consider putting it on there. Secondly, I've posted every score I have except for one person's score on quiz 7, which I'll fix tonight. You got to look at, oh, and the experiments are only through experiment 11. So 12, 13, 14 are not recorded yet. If by all means, I'm still thinking I'm missing extra quiz 7 scores. So if you took quiz 7, let me know. Like I said before, I forgot to record those before I handed them out. Just send me email. You don't need to send me a picture, but send me an email with their score on it. And let's see, that's it. By all means, it's an administrative task. It's really tedious. Entering numbers, blah, blah, blah. I probably made a mistake. Don't hesitate to say, hey, this is wrong. Please correct it. And okay, looking good. Looking good. We're almost there. Okay, so I actually copied part of this presentation from an old slide, and we've gone over most of the old stuff, but this slide was still sitting here. It was worth saying. It was something I used on the quiz today. It has to do with validity of operations associated with ripple carry adders. So there's the ripple carry adder is adding two things, and no matter how you use it, you always have to kind of consider whether the answer is valid or not, which means whether the sum output of the ripple carry adder represents a valid number based on the operation you're doing. So checking validity falls into two categories. If you're using unsigned binary numbers, what you're checking is the carryout. If it generates a carryout, that means it overflowed, and that means the sum bits are not proper. And by all means, the carryout is the nth plus 1 bit, but it still indicates the sum bits are not proper. Okay, if you're checking for validity on signed numbers, particularly with the radix complement numbers, you need to check the sign bits of the two operands and the sign bit of the sum, and that's going to tell you whether the output is valid or not. And I think that's it for that. Like I said, it was something that I leveraged on the quiz, so it's something kind of useful. So, the example problem of the day. Let's see if I can shrink this thing. Yeah, I'm having trouble shrinking it, so I'll shrink it from the other thing. Shrink, shrink. I need the space to solve the problem. Okay, so this is a problem. It turns out I think this is a very interesting problem because it's kind of strangely similar to the problem we did on Wednesday. So problem we did on Wednesday, I'm sorry, on Monday. So that problem was great problem, too complicated for an exam, but if you understand the material in that and the techniques in that problem, and as this one too, you'll be looking good for the final, at least for the lecture file anyway. Okay, so this is a problem that it's doing two things here. It's searching for the values of 53, and it's searching for the values of 47. And what's going to happen is someone's going to press a go button, and it's going to count the number of times 53 shows up. If it shows up 8 times, it's going to count the number of times 47 shows up. If that counts up 8 times, technically speaking, I'm going to turn an LED on. And so if that doesn't show up, if those two sets of 8 values don't show up in 1024 or less values, then I'm going to leave that LED off. So if I find those two sets of values within monitoring 1024 inputs, then I'm going to turn the LED on. Otherwise, I'm going to turn the LED off. And I think that's all I got on this thing. So the very first step is, of course, to draw the diagram on this thing. And it has a go signal. It has data. I think I'm going to change that. It has value. It has a clock. And as output, it has an LED. That's all it has in the output. And once again, the LED is going to turn on when I find those two sequences in 1024 values or less. Otherwise, it's going to turn off. Okay, so there's well, I might as well start this problem. Okay, so this is similar to the last problem in that I need two counters in this thing. One is an event counter. The event counter is counting the number of times I find a 53 or a 47. The other one is a counter that counts up to 1024. That's going to tell me how many pieces of data I'm examining. So I'm going to go ahead and draw those first. Those two counters. I'm going to try to draw a little bit neater today. There's a counter. I'm going to call it counter 1 and counter 2. This counter 2 that needs to count to 1024. So this is going to be a 10-bit counter. And this other counter needs to count to 8, so it's going to be a 3-bit counter. I'll put little names on here, even though, as you'll see as I do this problem, I'm not going to use these count values because I don't need to. What I need for this problem is the RCOs, and I'm going to go ahead and name these RCO1 and RCO2. Okay, so looking good on this thing. Remember, what I'm interested in is when these counters hit 8. And this counter hits 8, this counter hits 1024, which it's not going to hit 8, it's going to hit 7, and the RCO is going to turn on. This is going to hit, second counter here is going to hit 1023, and the RCO is going to turn on. So this, up here, this is an event counter, and so he's going to be dependent upon something else to control the up on this thing. So it's an event counter, which means I'm not going to always be counting up on this thing. So I need to occasionally hold this thing. So I need to put a note here. So when up equals 1, I'm counting up. When up equals 0, I'm holding. So that's for this counter right here. Okay, what else do I need of these counters? By all means, they're clocked. And I'm not going to draw the clock, but that little triangle looks good enough. I need to set these counters. I don't know where they are. I need to clear both of them. And looking good. Okay, so this top counter, it's an event counter. I need control over whether I'm counting up or not. I need to occasionally hold it if I'm not finding that event. But this lower counter is a little bit different. I know it's always counting up, and so I can just tie that to assert that up signal on there and always count up on it. Okay, I think I'm done with those counters. I can clear them. I got control over them, or at least the control I need. And let's go forward with this thing. Okay, so the event that it's counting is whether it's equal to one of the inputs. Okay, so that means I have a comparator sitting there. It's going to be comparing the input. It's going to be comparing the input to one of two values. Okay, so once again, I have one of two values sitting there. It's going to choose one or two of those values, which cries out wildly for mux here. Okay, so this is 0x53, 8 bits, 0x47, 8 bits, looking good. I know I'm going to need control over that mux. I'll give myself a control input there, and the other thing it's comparing it to is the input value, which is 8-bit. Both these are 8-bit signals, and I can't think of anything else. I think I'm done with this thing. Well, I guess I need a state machine now. All right. Okay, so here is state machine. So the thing that's going to control the state machine is going to be a go signal. And it looks like I need both these RCO1 and RCO2, these are status signals from the circuit. And so I know they're going to be, the state machine is going to read that status and do something. And what it's going to do is, it's going to send out a select. It's going to send out a clear. Notice the select and clear are control signals to these circuits. So this clear is a control signal. Well, the clear is a control signal for both counters. The select is a control signal for this mux here. And looking good. I think anything else? Of course, I need that LED. I'm going to control the LED via the state diagram. Okay, I think I'm done now. If I forgot something, I can just go at it. Okay, so I'm gonna clump through this circuit, not really knowing what I'm doing. Essentially, I'm not really super clear on how to handle that, 2 RCOs on this thing. So I'm gonna pretend like I'm not counting up to 24, and I'll go fix that once I'm done with my state diagram. So you're gonna find out. You're gonna see that I'm gonna start at one point and end up at another point here. Okay, so let's do this thing. This is my state diagram. Typical stuff that I do here. We got a go signal, no go signal. It does nothing. I get a go signal. It's going to clear those 2 counters. Okay, so in the meantime, what I'm going to do here is, oh yes, I forgot. The state machine has a reset sitting in it too, so I'm going to go ahead and draw that right now. Reset. Okay, so in the starting state here, I'm going to say, as the problem stated, it resets to the state where the LED is off, and I think I'm looking good on this one. What I'm interested in here, if I have a value for all these control outputs of the state machine for the state. I have a value for clear, I have a value for LED. Select, I'm not going to put a value for it because essentially it's a don't care. So I'm not going to junk up my diagram by putting that in there. Okay, so here's the oops, don't do that. Okay, so technical difficulties there. I'm going to call this the count 1 state. Count 1. Okay, so in this state, this is a state I'm looking for that 53, which is right here. I'm looking for that 8 times. So what I need to do is look for that 53. And so that means I have to get this properly selected. So in this state, select is not a I don't care. It's actually, I need to assign it a value. Okay, so clear. Also, yep, I certainly don't want to be clearing this thing. And I haven't found my value, so I'm going to turn the LED off also. So what I'm doing here is making sure from this state I've covered every case. Okay, and looks good. So I'm going to, remember, I know this is wrong, but I'm going to, this is actually the way I did it the first time because I wasn't really clear of how to do it right. So I essentially going to do it wrong and then fix it. because you know, once I do it wrong, it's going to show me things I wouldn't have seen if I hadn't done anything. And so this one is it's going to stay here so long as RCO1 is not asserted. Okay, that keeps disappearing. Okay, so the idea here is, let's say I get an RCO1, RCO1, and it's going to transition to the count 2 state. Count 2. They're freaking out. Touchy pen. Okay, so in this state, I'm looking for the second value, which is 47. So select is going to be on. I need to do it slower. I'm going to turn the LED off. LED. LED still off. and the clear's off. I don't know why the pen is freaking out. Okay, seems to be working here. Okay, so once again, from this dumb guy approach, I'm going to say I'm in this state. I'm looking for, I'm going to stay here so long as RCO1 is off again. And once I get an RCO1, I'm going to go back to beginning state. Okay, so roughly speaking, that looks kind of right, kind of sort of, but it's obviously wrong because look, the RCO, the LED never turns on. And each three of these states, the LED's off, so obviously there's something broken here. Okay, so the issue in this diagram is that I need a kind of a start state where the LED's on, and which is fine. So I'm gonna essentially put that there. I'm just gonna put the state there, and I'll go and fill it in a second. But this is going to be exactly the same as this other state. I don't know. I'll just call it weight X. Probably not the world's best name. But essentially, it's the same as the other state, but the LED is going to be on. Okay, so, and it's exactly the same. Go. And go. Clear. Okay, there's the same thing. Okay, looks good, but the problem is I don't think this transition here is right, but I'll fix it in a second. Okay, so I should have made that a little bit differently, but that's okay. Okay, so I'll go ahead and erase it because I know it's wrong. Okay, so we're going to back up here. I'm in this state. It's an event counter. So anytime these values are equal, it's going to cause this to count up. Okay, and the question is, well, should I clear the counter before it goes to count 2? The answer is no. It actually rolls over automatically. The RCO is going to turn on at 7, and then it's going to transition up on that next state because what turned the RCO on is a up signal. So it'll make more sense when we get that in here. So, but from this state, I need to consider RCO2 because this thing could time out. And so the idea here, if it times out, what's going to happen? Meaning timing out means I go to, the RCO2 turns on before I go anywhere. So this is RCO2. If RCO2 turns on, that means the 1024-bit or the 10-bit counter hit its maximum value without finding the two sets of 8 sequences, etc., etc. I'm off. I'm done. I go back to the beginning with the LED off. Okay, so that works. What what also needs to be fixed here is I need to include RCO2 in this diagram. Okay, there's RCO2, RCO2. So once again, okay, looking good. This pen is acting weird. Okay, so this is a now that RCO is included, it has to I have to use it to disambiguate these two transitions. If it wasn't there, it would be a question of what is RCO doing to cause a transition to back to this state or this state? I need to include these in here. And so the issue is that in this state, this count one state, I'm interested in two input variables, which is two status variables here. Okay, that means I need 4 different transitions. So this is one transition, this is the second transition, and this is actually 2 transitions, because in this transition right here, RCO1 is actually don't care. So I'm going to write it over here. So this becomes RCO2 and RCO1 plus RCO2 and RCO1 don't care. Okay, so I can actually take this little equation here and factor it, and it becomes RCO2. That's, once again, that's what little I know about factoring Boolean equations. Okay, so looks good. I need to deal with this second state, and so what's going to happen here is it has the ability to turn the LED on. Okay, and so when is it going to turn that LED on? Is this when I find 8 of these things, RCO1. I want to find 8 of these things, and this pen is freaking out. 8 of these things, and I haven't timed out on it. Okay, so this indicates I've hit my 8 count, and that means RCO1, I'm interested in RCO2 is going to be off. Okay, so I need to include RCO2 in these things. RCO2, there's my RCO2 up here. Why does it keep turning off? Pen's freaking out. Okay, so this is saying if it hasn't timed out, and I haven't found my 8 events, so it stays there. Okay, what this is saying is it has timed out. I mean, it hasn't timed out. I found my 8 events, and so I turned the signal off. Okay, so what the other transition here is on a transition back here when RCO I hit an RCO2, come on, stay in there, and RCO1 is off. Okay, so looking good, and so I feel like I'm missing a case here, and the case is going to be, well, let's review these things. I haven't got either of them, so it's going to keep looking. This is one where I haven't found the events and it times out, but in this case there's actually going to be 2 cases here. There's going to be the case where I do find the event and it hasn't timed out, but the other case is when I do find the event, RCO1, RCO2, RCO1, RCO1 and RCO2. Okay, look, check it out. It also is valid if the last piece of data I look at is actually going to be the 8th value that I found here, and that's these 2 cases here. And as someone definitely pointed out today, this is actually factors into RCO1. And that's the whole problem. So summary, the tricks in this problem, particularly as it compares to the problem we did on Wednesday. Okay, so on Monday, on Monday's problem, we had control over the up. We needed control over the up because the output of that counter was persistent, and we didn't want it to change after we were done doing the algorithm, etc., etc. In this problem, we're not displaying the count, so we really don't care what the up is doing after the algorithm is done. What we care about is the LED, and we've covered it that way. So if I don't need exact control over the event counter, I can just connect it directly to the EQ output of the comparator. Okay, now I could very easily have put this EQ as an input to the state machine and up as an output. It would have worked great, but I'm taking advantage of internal control on this thing just to simplify my state diagram a little bit. Okay, so the other thing in the state diagram is I guess I have to turn the clear off too. No, the clear is already off. I need to do that. It wasn't immediately apparent that I needed two kind of beginning states on this thing. I kind of figured it out as I went along. And the issue was I need to be able to have a wait state where the LED is on and a wait state where the LED is off. So I created two states here, completely valid. I'm trying to think of what else I need to do in this problem. What else is cool about this problem? I did put a note on this counter here. I can't think of anything else. I'm going to call it done. Yeah, so once again, this is not, the circuitry is not too complicated, like for an exam problem, but I would say the state machine is. The control of this thing is a little complicated. Once again, you're not going to see anything to this level of complexity on an exam, but I still think you should be able to understand this, and by all means, if you understand this, you'll be looking good for the exam. Anyway, that's all I had for this problem. Good luck, folks.